Welcome to our next lecture in the series on condensed matter theory. In this video I want to talk about topological insulators and topological surface states. In the previous video we have seen that we can classify materials by the topology of the wave function. For a material with either completely filled or completely empty bands, we can calculate the topology of the wave function for a given band. The wave function for each crystal momentum point can be seen as a complex vector in a Hilbert space. And this vector on the Hilbert space can have different topologies. Some wave functions define a vector field that you can, by adiabatically slowly move from one state to the other, whereas other states can have a vector field that defines the wave function, for example with a twist in it or a winding number in it, that cannot continuously be deformed to become equal to other wave functions. And when you cannot adiabatically move one state into the other, we will call them topologically equivalent. Now what I want to discuss in this video is what happens at the surface of a state that is topologically non-trivial, or at an interface between a state that is topological non-trivial and a system that is topological trivial. When you go deep inside the topological non-trivial state, then it doesn't matter that you have a surface. So here your wave function is topologically non-trivial. If you then have a surface and now you move far away from the surface to the state that is topological trivial, then there the wave function again doesn't matter that you have a surface. So at that point in space the wave function is topological trivial. Now when you move from the topological non-trivial to the topological trivial part, then there is a conceptual problem. You cannot slowly change your wave function from a topological non-trivial state to a topological trivial state. That's exactly how we defined topology. So at the surface something abrupt, something discrete must happen. The topology of the wave function changes. It's like having a sphere in which you punch a hole. You have to do that somewhere. And now we can think, what can we do to our wave function? And when I have a filled band, the topology of that band is always defined. So when I go from an insulator to an insulator, you have a system with filled bands, you go to a system with filled bands. There is just no way to do this by staying always an insulating state. You have to change the topology of that wave function abrupt somewhere. And the way we can do this is to realize that we only define the topology of the state when we have filled bands. When we have a metal, you can have partially filled bands and the concept of topology breaks down. So when I have a topological insulator in some part of space and a trivial state in some other part of space, then the way I can continuously move, or the way I can move from one to the other, is by having a metallic state at the interface somewhere. You can try to make that as smooth as possible, the transition, but there must be a metallic state in between somewhere. And actually that is very nice, because this metallic surface state is protected by topology. So you can make deformations at the surface, you can put disorder at the surface. Somewhere in there must be a metallic state. So let's see now by an example how this happens. First I will make a simple example where I'll take a tried binding model which is three-dimensional, and I put an S and a P band on a cubic lattice. And then later we have a look at some real materials where we have topological non-trivial states and then the surface states in there. And these surface states actually come with rather peculiar properties, entangling also the spin and momentum in these wave functions. So for our first model, we'll take an S band and a P band and a tight binding Hamiltonian in crystal momentum space, where here I show you the matrix. On First we have the dispersion of the px band, the py band dispersing in the y direction, the pz band dispersing in the z direction, and I only include the pp sigma hopping, so your p orbital is hopping in the direction of the p orbital, giving you a cosine-like dispersion. The s orbital is spherical, it can hop in all three spatial directions, and the hopping amplitude is ss sigma. ss sigma is smaller than 0, giving you electron-like bands. pp sigma is larger than 0, giving you hole-like bands. And then the hopping between an s and a p orbital to the right and to the left is of opposite sign, such that you get a sine-like interaction between them. If you look at the band structure, then you find here in red the S band, which shows your on the diagonal a dispersion for kx, ky, and kz, so that's a dispersion of 12 ss sigma, and then from gamma to x 4 ss sigma, from x to m 4 ss sigma, and on the diagonal again. The fact that this is not a perfect cosine-like dispersion is because of the interaction that we included in here, where the S and the P bands repel each other. Of course, they don't repel at the high symmetry points because there the sign is 0, but in between they repel each other and therefore are lowered. The P bands on the 111 direction have by itself all the same dispersion of 4 pp sigma. However, one of the three, linear combination of the three, can interact with the S band, and that's why you see that you have here this anti-bonding compared to the cosine-like dispersion that you would have without that interaction. And the same is when you go from gamma to x, the py and the pz orbital do not disperse, but the px orbital has a dispersion, and the px orbital can interact with the S band, such that you get here not just a cosine-like dispersion, but this additional repulsion between the levels. When you go from x to m, you move in the ky direction, such that the py orbital has a dispersion, the pz and the px orbital don't. And now I move back to gamma. If you now look at this band structure, where we change the on-site energy, so it's the plot here, epsilon s is below epsilon p, we now can make that smaller and smaller. You see that they start to overlap, and then at some point the S band is above the P band. There are a few points that I would like to point out. When we make the on-site energy such that the bands just touch, then you see that at the R point there is no gap opening. And when kx, ky and kz is pi, or pi over a, I make a 0 here in my equations, then the hopping is exactly 0, such that at this point your wave functions touch, or your bands touch, and there is no gap opening. Then when we continue, you have a crossing, the S band is now below the P band, and we see that once these bands overlap, we always have a metal. The S band starting at R goes to gamma and then slowly changes character into a P band. Then out of the 3 P bands, only one is interacting with the S band. The other 2 P bands have your cosine-like dispersion back to R, and at R this P band has the bonding and there the anti-bonding character going from P to S. So the moment your bands overlap, you always have a metal. And when we make the S band higher again, then at some point they are degenerate at gamma, and if you even make it even higher, the gap opens. You have this at R and gamma, which are the extrema of your bands. Of course, you also have this happening, for example, at the X point, when their energies, on-site energies, are chosen such that the bare bands touch. There is no gap opening at X, and if I make the on-site energy clearer, there's also no gap opening at M. Now, in order to talk about topological insulators, we need to have an insulator. And in this case, you can have either the case where the S band is above the P band. We put in 6 electrons per unit cell, that would be an insulator. But this would be a trivial topology. Or we can have the case where the S band is below the P band. We put in 2 electrons per unit cell. The S band filled, the P band empty. And also that would be a trivial solution. Once we have an overlap such that you can have odd bands, there is no gap opening such that it's always a metal, and therefore on this level we cannot make a topological non-trivial insulating state. In order to do that, we can add spin-orbit coupling to our system. We now have this Hamiltonian, this tight binding Hamiltonian for the states with spin up. We make a copy for the states with spin down, and then we add spin-orbit coupling. And the basis for spin-orbit coupling here is px with spin down, px with spin up, py with spin down, py with spin up, pz with spin down, pz with spin up. And then the dispersion of the px orbitals is here on the diagonal, the py orbitals is there on the diagonal, the pz orbitals is there on the diagonal. And then in additional to this Hamiltonian, we have our two orbitals for the s and the states with spin up. For the s interact with sin kx, sin ky, sin kz, with the state with spin up for the z, for the s orbital, and the same for spin down interacting with the spin down of the s orbital. So in total, your Hamiltonian is the spin-orbit coupling Hamiltonian on the p shell, a 6x6 matrix, the Hamiltonian, tight binding Hamiltonian with spin up, a 4x4 matrix, and a tight binding Hamiltonian for the spin down, a 4x4 matrix, that we in total have an 8x8 matrix, giving you the Hilbert space. We have 8 states, the 6 p states and 2 s states. Now if we diagonalize this, then you see that compared to the previous bands, here again the bulk bands, the p orbital split into a p1/2 and a p3/2 band. We now have a twofold degenerate s band, a twofold degenerate p1/2 band, and a fourfold degenerate p3/2 band. And when we now make a crossing between the bands, we are able to open a gap. So let's see what happens if we change the on-site energy such that the S-band slowly moves on top of the P-band. And indeed we see that several cases we have gap openings. So first of all, when we make the on-site energies such that the S and the P-band touch at R, then again, because your interaction is sin kx-like, sin kx, sin ky, sin kz-like for the px, py, and pz orbital, there is no gap opening here. So the moment they touch, you're actually in a metal. Then once we go beyond that, now we have here at R your band inversion. It's inverting with a twofold degenerate band such that we can have a gap opening, and exactly that happens. So now we have here a band that has even character at R, odd character at gamma, x, m, and gamma. And if we now calculate the parity of this band, then we can have a look at the behavior of our Bloch waves or Bloch states at the high symmetry points, the time reversal invariant momenta points, which is R, gamma, x, m, and gamma. We have the inversion at R, so this wave function here that we have is odd. So if the Fermi ladder would be such that we have 2 electrons per unit cell, then this tight binding Hamiltonian would give rise to an odd wave function that is topologically non-trivial. So if you then calculate the Berry phase by winding around the Brillouin zone, you will find that Berry phase is pi instead of 0. Then if we increase, my video is moving, even further, then at M your bands become degenerate. And then we put the on-site energy of the s orbital even higher, and we now have an inversion both at R and at M, such that the parity of the lowest band becomes even again. We have 2 even and 2 odd states, such that into trim points, such that in total everything is even. If we then increase the on-site energy of the S even more, we touch at the X point and we get an inversion at the X point. And once we have an inversion at the X point, the gamma point is even, all other points are odd, such that our total wave function is odd again. So you're alternating between even and odd states for the ground state wave functions. And the evens are topologically non-trivial, the odd states are topological. The even states are topological trivial, the odd states are topologically non-trivial. And now we can increase the on-site energy even more. At some point you will also cross at gamma, and then our ground state wave function is made out of fully odd states at all time reversal invariant points, and therefore becomes even again. And well, at some point the S band is completely above the P band, and everything is normal again. So now we can have a look what happens at the surface of such a system. So for this we can set up Dyson's equations, truncate the state at the surface, and calculate the surface projected bands, or calculate the surface Green's function of a semi-infinite crystal. So if we look at the surface Green's function of a semi-infinite crystal, then we go from gamma bar to x bar, from x bar to m bar, and from m bar back to gamma bar. We here see the cosine-like dispersion. The dispersion in the z direction now is projected onto the the dispersion in the z direction is broken because you're no longer periodic in the z direction. So we see the full bandwidth that we have in the z direction here in a single plot. You get more spectral weight at the bottom of the bands because this S band is antibonding with the p orbitals. In red we have the s orbital, then the px and py orbital are non-dispersive in the z direction, so these show in green here are just the normal dispersion that you would have in your crystal as well, because there is no kz dependence. The pz orbital has no dispersion in the x and y direction, such that it becomes this blue band where you basically fully integrated over the kz dispersion, and in the x and the y direction you're constant. And the fact that it's not entirely constant is because we added spin-orbit coupling, which also then leads to this gap opening that we have, plus that we have an interaction between the p bands and the s bands. If we now reduce the on-site energy between the s orbitals and the p orbitals, we see that the s orbital is climbing, and we also see that inside the gaps surface states emerge. So we increase, then at some point at m bar your bands start to cross or touch. Well, actually that is at the R point in the Brillouin zone for the bulk bands, but well, if you project that onto the surface, then kz, of course, well, the bottom of this red band is kz is 0, the top is kz is pi, and here you have this touching, and then when you make the on-site energy even larger, a gap opens, and inside this gap we have this nice cross and a surface state. It must be a metallic surface because you transfer from a topological non-trivial state into a topological trivial state. If we then increase the on-site energy even further, we nicely see now that you have your inversion, and the S band is above the P bands at this point, and you get a beautiful surface state in the gap. Then at some point your bands become degenerate at x bar, and then you also have the crossing at gamma bar, and we see that again here you get a nice surface state inside the gap opening, until at some point the P band is completely, P1 half band is completely below the S band, and you're just a topological trivial system with no gaps and or with no surface states inside the gap. Actually there is a surface state here, but it's not filling in the gap between them. And then the S band is completely above the P band. Now if we look at such a surface state, let's take the one around m bar, or here the one around gamma, then we see that these form such kind of crosses at all points. And we can understand why that happens. We have spin-orbit coupling in our system, but we also have inversion in the bulk. So space inversion tells you that the state at k with spin up must be degenerate with the state at minus k with spin up. We have time inversion in our crystal. So time inversion tells you that the state with k up at spin up at minus k must be degenerate with the state with spin down at plus k, such that when you have both space and time inversion, you will have a degeneracy between k up and k down, with spin up and spin down at each k value. So in the bulk, we see that although we have spin-orbit coupling and a Hilbert space of 8 states, we only have 4 bands, and each band is twofold degenerate. When we then go to the surface, then at the surface there is no inversion symmetry. So we can lift this degeneracy between the state at plus and minus k. And that is exactly what happens here. At your trim points, the space inversion brings k back to the minus k and plus k are equivalent, such that you still must have a twofold degeneracy at these high symmetry points. But when you move away from those high symmetry points, you can lift that inversion. Now we still have time reversal symmetry. So the state at k with spin up must be degenerate with the state with minus k with spin down. But spin up and spin down don't have to be degenerate with each other anymore. That means that there is an entanglement between the spin, or a relation between the spin that we have at each momentum point and the crystal momentum. So here you get around your high symmetry points. And crossing of your bands, where at the high symmetry points your bands are degenerate, and away from the high symmetry points your state is one-fold degenerate with spin in a certain direction, and depending on the crystal momentum the spin will be in a different direction, always such that k and minus k have opposite spin directions at the same energy. Now this happens not only in these kind of cubic models where we can nice and easily calculate the tight binding Hamiltonian, but this has been also found in real materials. And bismuth 2 selene 3 is one of the semiconductor materials where you find these kind of topological surface states. Here in green we have the bulk states at the surface, so integrated over kz, and then in orange we have the additional states that you have due to the surface, or that are close to the surface, and we see that inside the gap there is this nice surface state forming, twofold degenerate at gamma, but away from gamma single-fold degenerate with a clear relation between the spin and the crystal momentum. If you look at this surface state, then this forms a two-dimensional electron gas with a linear dispersion as a function of crystal momentum, and a spin crystal momentum that is basically the spin vector is perpendicular to the k vector running in a circle around the Brillouin zone. Now this is something you can use if you want to make spintronics. Then you know that a particle that's moving in one direction always has a particular spin related to it. So if you make optical excitations, then the dipole moment will drive electrical charge in a certain direction, and with that you drive spins in a certain direction and therefore start to magnetize your sample. So if you want to make devices where spin and charge degrees of freedom are coupled to each other, or where you can play with the spin, then these kind of two-dimensional electron gases are very suitable for that. It's also nice that if you have some distortions, you will not destroy this two-dimensional electron gas because you're topological protected. Now if we look in a bit more detail at our surface state, then bismuth to selene 3 is given by layers. We have this triangular layer of selene, then a triangular layer of bismuth, a triangular layer of selene again, a triangular layer of bismuth again, etc., etc. And you have these 5 layers, and then the unit cell repeats again. So selene, bismuth, selene, bismuth, selene, and then selene, bismuth, selene, etc., etc. So it is these blocks that form a unit cell, and then this layer repeats below here. So this layer is not equivalent to that one, but you have 2 layers of selene after each other. We can now have a look at the wave function of our surface state that is bound to the surface. So we look at the wave function that we have the eigenenergies somewhere here at the blue circle. And then you find that if we just look at the pz character of your wave function, that the first layer has a strong pz character, and then it is getting smaller, and the third layer has almost no character, but then the fourth layer has again some pz character. So this is not a delta function as a function of kz, but your wave function has some shape. It's bound to the surface, so when you get deep inside, it's nicely exponential decaying, but you take a few layers, a layer of 5 or so, before that wave function is formed. Now we also put in some color here, and that color is related to the expectation value of Sy. So you see at this point it's pointing in the minus direction, here it's pointing in the plus direction, and in between it's pointing in the x direction, such that Sy, the expectation value, is exactly 0. So your spin is rotating around the Brillouin zone. Now, we do not only have py character, we also have some in-plane character of these orbitals. And you actually see that when in the third layer there is no pz character, there is some character in the other orbitals. And for the other orbitals, you might have a spin that is rotating in the opposite direction, or there might even be some entanglement between the px and py orbital and different spin directions inside there. You can actually explain here the opposite behavior, because if you think of spin-orbit coupling, then a pz to a px orbital is an L plus operator, and L plus comes with S minus, such that you flip the spin when you change the angular momentum, and you get these kind of relations between the spin and the different orbitals. But in total you see that, well, the wave function is much more complicated than just a single layer, the single delta function. That's a pity, but that's reality. If you would have a perfect delta function in the z direction, you couldn't scatter from k to minus k, because then the spin had to flip. Well, at this point you can of course scatter from k in the first layer to minus k in the second layer. And therefore, or from k in the pz at the first layer to the px in the z first layer. Well, and therefore you do have backscattering, so your conductivity is not infinite, but nonetheless you have a surface layer that is metallic, conductivities are reasonable. So the total wave function then has a look like this. Yeah. So with that, I hope to have shown you some of the properties that we have for topological surface states. You have beautiful entanglements between the spin and the momentum in which you move. You get dispersions that are linear with respect to crystal momentum around the high symmetry points, such that you get cones. You can call them Dirac cones if you want, according to the massless Dirac Hamiltonian. We have spin up and spin down mixing with decay vectors. If you put in distortion, you stay nicely metallic, because these surface states are projected by topology. Thank you very much for your attention. We see each other later. Stay healthy.